The next one is a generic abstract syntax model for embedded languages by Emil Axelsson.
Okay. Do you hear me? No. Do you hear me now?
Yep.
Yes. So, I want to just show the big picture first. So this work is, the overall goal of this work is similar to what you heard Kunlo Lukutan talk about yesterday, namely to make it really easy to implement domain-specific languages. And ideally, you should be able to assemble a DSL implementation from a set of predefined building blocks. And by the way, when I say DSL, I really, in this talk, I mean a deeply embedded compiled DSL. So that limits the scope. If you look at different DSLs, you find that they often have a lot in common. There are similar constructs, and inside the implementation, there's also similar functions operating on the expressions. So there is really opportunity for reuse. And we often hear that Haskell is a good host language for embedded DSLs. And I guess that's generally true, but at least in my experience with compiled DSLs, there are quite a lot of things you need to deal with if you want to make a realistic DSL. So how to deal with variable binding, how to recover sharing, and so on. And to get all of this right actually is non-trivial, and this is something that people re-implement over and over again. So there's a certain reusability issue here, and it boils down to two main parts. The first one is that the expressions are usually modeled as closed data types, which are not compositional and not really reusable. And the second problem is that the functions operating on ASTs are normally not defined as generic functions, so they cannot be carried over to different implementations. So in this work, I propose a generic data type model which you can use to encode ASTs. And it gives you direct support for generic traversals, and you can also use it to compose language constructs. And here it is, the whole model. It's the type called AST, which is really nothing but an application tree. So we have symbols and application. And if you ignore the colon before the arrow, let's see up here, and if you ignore the full type constructor here, you see that it's really an application operator. And if you're interested in what colon, arrow, and full are used for, you can find more details in the paper. And to introduce a symbol, we have this DOM type. So symbols are taken from this type, which we call the symbol domain. And by using different domain types, we can encode different languages. That's the basic idea. And as an example, here's a simple type of arithmetic expressions with numeric literals, addition and multiplication. And here is the same type encoded using AST. So we have num, add, and mul. These are the symbols. So yeah, so Arath is now the symbol type. And if we look at add, we see that it has no arguments. Instead, it has this phantom type signature that says that it expects two integer sub-expressions and returns an integer result. Num is slightly different here. We have an actual argument because we're lifting an actual Haskell int to an expression. But otherwise, this is how symbols are defined. And then we say that expr is an AST with Arath as the symbol domain. And this gives us two types, expr prime and expr, which are isomorphic, so we can convert back and forth between them. And to see how to construct such encoded terms, we can make smart constructors for these symbols. For example, in the add case, we say introduce an add symbol, apply it to the first sub-expression, and apply it to the second sub-expression. Nothing strange there. Just a tiny example written in both languages. So we can program with this encoded expression type as with the reference type. And we can also pattern match on expressions. So here's just a standard evaluator, a recursive one for expr prime, and on the bottom we have the same evaluator for the encoded language. And the only difference really is that we have to match on sum and colon $. Otherwise it's really the same thing. And it's also important to see that we have the same type information available in both definitions. When we pattern match on add here, we get the same local constraints as we do up here, that we have integer sub-expressions. So, what we have done so far is to see how to encode recursive GADTs using these simpler symbol types. And we can program with these expressions almost in the same way as with ordinary GADTs. But there's some overhead, but not very much. And we have the same type safety. So now the question is, of course, what's the point? Is this just another way of doing the same thing as we could already do with ordinary GADTs? No, we can do much more here. And the key observation is that the symbol types are non-recursive. When we're using the AST type, the only recursive, it's only the AST type that's recursive. The symbols are non-recursive, which means that we can traverse expressions without referring to the symbols involved. And this will give us generic traversals. And since these types are non-recursive, we can also compose them using type level sums, which gives us composable data types. So here's a simple generic function to count the number of symbols in an expression. If we have a symbol, we return 1. If we have an application, we just add the sizes of the sub-expressions. And this, as we see, this function is completely polymorphic in the domain. So whatever language we choose to implement, to encode using AST, the size function will work for that language. So it's a fully generic function. A slightly more interesting example is to find the free variables in an expression. So free vars takes an expression and returns a set of variable identifiers. But in this case, we have to know a little bit more about the domain. We have to know which symbols are variables and which symbols are binders. And that's captured by the binding class, which has a function viewVar that checks if whether a symbol is a variable, and in that case returns its ID. And the view BND, which checks if a symbol is a binder and returns the ID. And here the idea is that the binder has a sub-expression, and the variable is bound in that sub-expression. Okay, so in the definition, we use view patterns to make it fit nicely in one pattern. If we have a variable, we return the singleton set with that ID. If we have a binder, which binds variable v in the body, we get the free variables of the body and delete v from that set. For any other symbols, we have the empty set, and if we have an application, we just take the union of the three variables of the sum expressions. So here we have to make some assumptions about the domain, namely that the domain implements the binding class, but this is really a minimal assumption. So there are lots of types that can implement the binding class. And again, there is some overhead. We have the sim, the colon dollar, we have the view pattern, but it's not all that much. And really the definition is it's a straightforward recursive definition in the way we want to program. Okay, that was generic traversals. So now let's see how to compose data types. And for that we use a type level sum, which you might have seen before. So what this what the plus does is to just combine two symbol domains, and we use inject left to introduce a symbol from the left domain, and inject right to introduce a symbol from the right domain. So now we can build up symbol domains by just adding smaller symbol types. So here's an example where we have a type A plus B plus C, and then we have Arath somewhere in the middle. But the problem with this is that now the overhead increases. So to introduce an addition, we now need 4 injections because Arath appears deep inside this sum here. And that's not so nice. But fortunately there's a nice solution to this problem, which we can borrow directly from data types a la carte. So the int function so it's a type-directed function that, based on the types, will just insert the right amount of injections. So now we can just say inject addition and apply it to its argument. And then we get this constraint up here, which can be read as the domain should include Arath. So the domain can be a sum type where Arath appears somewhere. And again, this is really a minimal assumption because there are many domains which fulfill this constraint. So let's try to extend the Arath language with variable binding. For that, we introduce a new symbol type with a variable symbol and a binding symbol. And we make smart constructors using int as before. And now we have everything we need to write an example like this one. A top-level lambda and an arithmetic expression involving some variables. And this is how it looks. We have the lambda, and we have addition of variable, and so on. And the type here now says that the language is arith plus lambda, so arithmetic expressions with variable binding. So now we want to use the freevars function that we defined earlier to find the free variables in this expression. But to do that, we first have to explain what the symbols mean. So we give instances for the binding class, and the interesting case is, of course, the lambda type, where the view var checks if we have a variable, we returns ID, otherwise nothing. And similarly for lamb. Here's the same example again, and it works. So now just remember that freevars is this very general, very generic function that doesn't know anything about the language it operates on. All it knows is that this is the language that has variables and binders. And it always works nicely together. Oops. Let's see. So this ASD model is available in the Syntactic library, which you can find on Hackage. And the intention is that Syntactic should be this general library of building blocks that you can use to implement DSLs. But I should say that there's a lot of experimental modules in this library, so it's still work in progress. But at least the core part with the AST type and the functions around that part is quite stable now. And as a practical use case, we have the feldspar DSL, which you've heard mentioned a few times, which is now implemented using Syntactic. So feldspar is a language for high-performance numeric computations. And there's also a toy implementation of feldspar included in Syntactic, which you can have a look at if you want to know more about how to use Syntactic. Okay, to summarize, the overall goal was to define a generic EDSL library, and for that we need to be able to define syntactic constructs independently and compose them, and we also need to be able to define generic traversals over such expressions. And the AST types lets us do both of those things. Thank you.
Thank you.